Can you hear me? All right. So last time, after some work, we ended with this picture that summarizes the vacuum structure of the standard model. And I think a main reason why I like this is because this structure is actually rich and non-trivial, like you saw. Even today at so-called zero temperature, when there are no some interesting cosmological particle dynamics going on, just the structure itself is non-trivial. And roughly speaking, it looks like this. If you plot the effective potential now, let's call it V0 plus V1, the one loop correction of the potential as a function of basically the Higgs field, then it has this fun structure that there is the electroweak breaking minimum where we live. This is us. And there is this local extremum, this local maximum up here. This is us at phi c of 246 GeV, measured in ways that Christophe explained. But then the structure is really interesting. There is a huge barrier, but then the potential turns back down. And in fact, we can measure the structure by measuring local properties and interactions of the model that we do these measurements over here. And we can see the structure is most likely something like this. And that is what this plot is summarizing. This plot is summarizing that, for example, this dot here, this little point here is the experimental uncertainty. That's the region that was measured. This region is called here metastability. Here there is one parameter alpha s on the x-axis. So alpha s is the strong gauge coupling squared over 4 pi. That's a definition. There is a similar definition for electromagnetism and so on. And the y-axis is the top mass is the mass of the top quark proportional to the Yukawa coupling. Here there is a similar plot with the top mass or Yukawa as a function of the Higgs mass, or lambda, the quartic coupling of the Higgs. And here the point is that one little one over here. These are zoom plots. And you see that we live kind of nicely inside of the metastability region. Below us is absolute stability, and above us is instability. A comment to just reiterate again, we discussed this a lot yesterday. New physics beyond the standard model could change this picture a lot. It is nevertheless remarkable that even in the standard model alone, we have this interesting situation. And the yellow region says that in the yellow region, the potential is like that. Why don't I make this yellow? So this is the situation that is called metastability. Metastability says, you live here. Over here, there is another local minimum that is even deeper than us. In fact, the cosmological energy density, if we had lived in this region, would be negative. The cosmological constant would be negative because on this side, it is so tiny. And then there is the red region that is called instability. I actually have a little bit of red. The red region would be the similar qualitative picture, but then the red goes deeper inside. Deep enough, the tunneling is faster than the age of the universe, and then it would be expected that within a short time, the state put here would tunnel over here. And so this picture seems to be inconsistent. And then there is the green. Do I have green? I have blue. The blue is something like this, where there can be an interesting structure, but this local minimum is higher than us. It has a higher cosmological constant than us. So I like it because this rich structure is in the standard model. Sorry? The blue is green. Yes. So the blue is absolute stable. There is nowhere to go. This has higher energy than this one. This is unstable. And this is where we most likely are, as of LHC measurement. This is metastable. Now, I didn't mean to talk too much about this process of what happens if you live in this metastable configuration, but I'll talk about this a little bit, because it's a very interesting topic. I won't do any serious calculations about this, but just to ask ourselves, what is this kind of situation? And again, this is in the standard model, but many people nowadays are trying to think, if there are more scalar degrees of freedom in the model beyond the Higgs of the standard model, then there would be additional scalar directions. So this potential, you would extend it as a manifold or a function in several dimensions. Each dimension would be another kind of Higgs or another scalar field. The structure could be very rich. For example, if grand unification is not an illusion, if there really was grand unification very early in the universe, then there are more scalar field directions, and they have interesting structure, and in fact, they are spontaneously broken, just like we are. And then there is a lot of discussion about phase transitions in the very early universe. Maybe they can do gravitational waves, and so on. You read a lot about this. Well, hey, the standard model can, in principle, do this as well. So suppose that we really live in this yellow region, right, that the measurements are correct, and in fact, the standard model is correct, or modifications to the standard model are not significant enough to change this basic result. Yes? Yes?
Was it always like that, or it evolved with the expansion of the universe?
So the question is this shape time independent? The answer in a way is yes. The structure of the quantum classical and quantum structure of the potential is just the way it is. It could change again if there are more field direction here. Then it could be that we effectively have some objects here that we think as constants, for example, the mass parameter of the Higgs, actually contain in them a contribution from vacuum expectation value of some other scalar. In that sense, if that other scalar moves around, then you might find yourself in a different patch in this manifold or structure of the potential. That is possible. So in this sense, and if symmetry breaking moved from vacuum to vacuum, you might find yourself in another place. But the structure itself is there. You were just living in another place. What we will see, and these are the main calculations I want to do today after this small discussion, is we will see what happens to the state when you add high thermal energy density. In the very early universe, there was many interacting particles that were flying around, and then they would change the way the field behaves under this vacuum. So in a way, effectively, the structure would change at high temperatures. You will see it. But in another way, the quantum and classical structure stays the same. There is just another correction because of the state. So the structure is the same as the quantum field theory structure. The state can differ. The thing to understand is us being here is a statement about state. What does it mean, this statement about state? Actually, let me show you a movie. Why not? Of the meaning of tunneling in quantum mechanics. Because if I put us here, if the state of the Higgs field is such that, on average, in the universe, it is constant and located at this point, right, phi c, then this is a statement about the wave functional of the universe, right? Field theory has, quantum mechanics has wave functions. Field theory has wave functional, which is the same, but with infinitely many degrees of freedom. And the statement that we're here says that the wave functional is concentrated around the field configuration that is very simple, just the constant at the point. This wave functional, the ground state of a system like that, in fact, has a Gaussian spread around fluctuations that live around this phi c. These are exactly 0-point fluctuations that you're familiar with. So, but there is a Gaussian, you can interpret it as a Gaussian spread around this constant field configuration. The analog in quantum mechanics of this kind of situation, where we think we are, is that suppose you have some potential. Here, the black line is a quantum mechanical one-dimensional potential. Okay, think quantum mechanics, a particle in a box. And what I did, you see, my potential, the black line, has a little dip, like a potential well. And then there is an open region. Now, in a more interesting situation, the open region actually will go down. It will be a little bit below. So this situation has, the open region has, if you want, the same vacuum energy or the same level of the potential to the right and to the left. I did this just to make my calculation easier. The really interesting situation is that you have a barrier, and then the thing on the right is a bit small, is a bit lower. Like here, you have a well, and the other region is a bit lower, has a smaller vacuum energy. But the process is going to look exactly the same. And what I did, I took, if you can see, there are many lines here, but there is a black line in particular, which is the bump on top. I went ahead and I put a wave function, quantum mechanical wave function, for the position of the particle inside of the well. This wave function, the black line, it's the topmost one, is just the ground state wave function of this potential if one ignores the fact that the potential has this drop. So mentally in your mind, imagine to yourself that all you had was this little dip, this little well, and the potential here on the right just went on flat like it is, without the free region on the right. If you do this, you can solve the quantum mechanics problem of asking yourself, what is the ground state wave function in this well? And that's the thing I started the theory or the state in. Okay, it's the black. This is what we think happens in the field theory, where you have a wave functional concentrated around the well. Now, what will happen when I let time go? It's easy to see. Oh, it wasn't even on the beginning. I see. This is why it was hard to see. Great, my ground state and everything I said. This is how I start. Now, that's the top panel. I'm going to let time run. And what I'm doing, I'm simply solving the one-dimensional Schrodinger equation to see what the wave function does. You more or less know what it will do. What it will do, it's going to leak. It's going to tunnel to the right. It's going to tunnel because the energy of this would-be ground state, it's an approximate ground state because it's a ground state of the Hamiltonian, not the real Hamiltonian, but the Hamiltonian without this free region, right? So it's not a real Hamiltonian eigenstate, and therefore it will evolve non-trivially in time. And the way it will evolve, it will leak to the right. You know this. So what I did on the bottom panel, I wrote down log of P. P that I wrote, this P is just the probability of the particle to be found inside the well. Okay, so P is just the integral on the well, roughly speaking, this region. Dx psi of x, well, x and t squared. And I start our lives with p equal 1. The wave function is entirely or exponentially to an exponential accuracy concentrated inside of the well. And so this plot begins at 0. Log of 1 is 0. Yes? And now let's let time run. I may discuss this or may not. I don't know. So let me solve this Schrodinger equation. Here is what is happening. What is happening is the thing you know. Let's start. So a lot of things are happening here, right? But let's look at here. So look what is happening. The red and the green curves are the real and imaginary part of this wave function. So the real and imaginary parts are oscillating. The real and imaginary part would be oscillating even if there was no tunneling. It's just the e to the minus IHT, Hamiltonian t, so that is oscillating. This oscillation doesn't change the envelope, which is the sum of squares. However, what just happened, I don't know. Oh, maybe I pressed back. Never mind, it's fine. However, in addition to this oscillation, you can see if you look very carefully that there is a little wave, real and imaginary components, that begins to propagate to the right. It propagates in a causal way. The evolution in time of a quantum mechanical wave function is completely deterministic. As you know, quantum mechanics is fully deterministic theory of wave functions. Observables are now random. You need to calculate them with the laws of quantum mechanics using these wave functions. So this wave is propagating. Again, I did it. Nice. But it's OK. It has only 2 states. So the wave is propagating. As it is propagating, probability is leaking. And very slowly, the amplitude decays. Look at log p as a function of time. There is an initially slightly complicated behavior. And then there is a linear decrease of log p as a function of time. This linear decrease, it says that p, this object, is equal to p naught times e to the minus, well, almost equal, e to the minus gamma t, with some roughly constant rate gamma, right? So if you take the log, you get minus gamma t when p naught is 1, right? So for us, p naught is roughly 1. So the log is roughly minus gamma t, so it decays with the constant coefficient gamma as a function of t. Let's do another little thing let's look at another little thing here. As you do this, what I'm plotting in the lower panel is the probability current. That's the flux of particles. And you can see it's building up. There is some numerical noise because my potential is easy to understand, but a little bit hard to integrate because it has this step function. So the current is basically up to some factor of 2, I psi star dx psi imaginary. This is the probability current, just the momentum flux or particle flux to the right. Great. This is tunneling. You all know it. What does it mean in the field theory picture? Let me stop it somewhere in the middle as it is going. Our understanding of tunneling in quantum field theory is very partial and limited, but to the extent we understand it, it's very similar to what is happening in this quantum mechanical picture. We're actually using the same tools to understand. Can I pause? The state which has this flux of probability going to the right is essentially a plane wave. If you were to put a momentum measurement in some region, here on the right, you would find particles that are going with very roughly the same momentum. The momentum is the momentum that's equivalent to the 0-point energy of the object on the left. So these particles have, this wave is essentially e to the ikx with a given k, fixed k, just flowing to the right. What happens at the edge where the wave function didn't manage to get is complicated. It's very hard to analyze exactly in infinite dimensions like in quantum field theory. But that situation where you have wave function that's just a plane wave moving to the right with a slow exponential decrease of the probability, that part you can understand with semi-classical methods. That's what those of you who studied this, Coleman and Kalan, for example, studied in quantum field theory. And Coleman and De Lucia, we'll discuss this later. And so this is really the region of the calculation accessible to semi-classical calculations. What does the measurement look like? What does physical reality look like when the system is in this state? And you should understand, us living here in a state that is probably close to the ground state means that our wave function is leaking. It is leaking as we speak. It just so happens that you and I live at the realization of the system right now where we contribute to the probability still in the false vacuum. But our probability is leaking, okay? It is leaking away. What does it mean that it's leaking away? What would it mean in quantum mechanics? In quantum mechanics, it would mean that if you went ahead and measured properties of particles, there are a lot of particles here, or a large probability to find a particle here at nearly the ground state of the false vacuum. There is a small probability. You see, the wave function is small, right? So there is a small probability proportional to gamma to find the particle here in a given momentum state. In fact, it's a nice exercise to write a phase space distribution or a Wigner approximation to this state. It's very easy. We can do it if you want in Q&A. And you will see that the classical state that corresponds to this wave function approximately is this following state. It's like the device here is shooting particles randomly with an exponential rate, e to the minus gamma t. And each particle that is being fired, the time of emission is distributed exponentially, like I said. Each particle is actually just a free propagating particle at the fixed momentum, the momentum that is in the false vacuum. Okay, so this system looks like it's firing particles out at a random rate. Each particle is essentially classical when you find them. The analogy of field theory, the analogy of the particle moving classically as just a particle with a definite momentum in the free region is a field configuration that is expanding, solving classical equations of motion of the field, and taking the following system. Suppose you look at the box of space of our universe, and you waited some time, then there would be some probability, unlike this 1D quantum mechanics, our space has 3 space dimensions. And so tunneling can occur anywhere within these space dimensions. Somewhere inside of this space dimension, a tunneling event occurs. In semi-classical approximation, it looks like this kind of bubble of true vacuum forming in a sea of false vacuum. Once it forms, it can only form by a quantum mechanical fluctuation, but once it forms, it begins to expand, solving classical equations of motion for this state. The rate of nucleation of these bubbles can be computed, can be estimated in similar tools that you can estimate this rate. So the rate of nucleation, let's call it gamma, is, or let's call it, in fact, the n bubble by dv3, let's say, dt. The rate per unit volume per unit time for a bubble like this to form looks like some number. Let's call this number m to the 4, e to the minus s, where s is the quantum action for the formation of a single critical bubble. And m to the 4 is, you know that it needs to be here on dimensional grounds. Okay, so the number of bubbles is a dimensionless number. If you take this prefactor and multiply it by 3 space times time, it needs to be dimensionless. And so this is some parameter of order mass that corresponds to the details of the details macrophysics of the system. S is the action for a trajectory that tunnels. The bubble forms here, and then the rolling down is basically the expanding solution of the bubble. Okay? Yes? Literally, we think, that question was, what does a bubble physically mean? We literally think that the picture that describes this bubble is that, let me just give different names to this, false and true. Here, phi, expectation value of phi is 0. If you went ahead and measured, you can have a detector that measure phi. It's possible in principle. For example, your detector can measure, is the top massive or massless? You can measure that. So measure it here in the bulk, the top is massless. If you have been swept by a bubble, then in here, phi is phi c. It's near the vacuum. So in our case, well, I call this phi equals 0, right? So in our case, this is not really phi equals 0. The state of the false vacuum is us. Okay, erasing on mine, expectation value is v, is our vev. And in the true vacuum, expectation value is somewhere in this region, and then rolling down. So there literally is a spherical region of space that forms by quantum fluctuations. The very details on exactly the moment of appearance we do not understand. Semi-classical approximation does not allow us to compute it. It gives us a shape, which is spherical, but we shouldn't trust it. I mean, we don't understand the calculation, but it's roughly the shape. But inside of this region, the vacuum expectation value is close to here. And then this thing expands, very quickly getting to the speed of light. That's a topic that I love. It's dear to my heart, but I don't want to discuss here so much. Okay, it's enough for me that we get the qualitative picture. So the bubble expands. You wait a little bit more. It expands roughly at the speed of light, converting more and more and more space into, so this goes at the speed of light, v equal 1, converting more and more space from false vacuum into true. This is what the system is.
Professor.
So the analogy of a particle, that you would catch a particle in 1D QM with a given classical momentum, solving the equation of motion of a particle, the analogy of this is that you encounter a bubble, which is a classical solution of the field equation of motion, that is expanding and converting space to true space. There was another question? Yeah.
Does this transition always happens? Because when you study first order phase transition in the early universe, you have some conditions to this nucleation not fail. I mean, not the bubbles begin and then collapse.
That's right. I did not compute it. Is it a question or?
My question is there any other conditions to this phase transition happens?
There was not, strictly speaking, a condition. So what was mentioned here is that the original appearance of the bubble manifests some, again, it's our semi-classical approximation to the process. In principle, even before bubble formation, space is full with quantum fluctuations. Some of them convert a little chunk of space to be near the false vacuum by quantum accident, right? There are these fluctuations around. If these fluctuations are too small in space, they will be quenched back. They cannot materialize. They don't really appear there. This is a quantum state. It's not that it appears and shrinks, not in a way that at least I understand. It cannot go on shell. What is special with the critical bubble, we think that these bubbles that can materialize are bubbles that are such that since the initial energy was 0 or was any constant of this state, define this energy to be what you want, you cannot just go ahead and take a chunk of space and change the field as you want, violating energy conservation. You cannot. A state that can occur on shell is a state that has the same energy as the state that was here before. So you find that there is a critical size to the bubble. There is so-called a critical bubble, a solution to the equation of motion that can go on shell. From that point on, it can expand solving the classical equation of motion, but it has 0 energy. And it has 0 energy because you see in the bulk of the critical bubble, the fields live somewhere here, somewhere near the true vacuum, so it enjoys a little bit of negative energy, right, this energy gap. But in the boundary, the field is changing. It's changing from false to true vacuum, so there must be derivatives that are non-trivial, and so you pay positive kinetic energy. The critical bubble is this configuration where the positive kinetic energy and the negative bulk energy exactly cancel. Okay? So there is a critical bubble, and from there you expand. So if this was the question, it's true.
Okay. Other question is, when you change the vacuum, you change the particle mass.
Yes.
Where the energy goes to?
You mean what happens to all the particles that are flying around?
Yeah, they are changing the masses.
Fantastic. That's exactly what I want to actually calculate.
Oh, okay.
So let's calculate.
Yeah,
the question was the follows. It's a very natural question to ask. It's a very natural question to ask, especially in the early universe. Well, so today the state of the system, we have particles, right? We have galaxies. Galaxies are particles. They're full of protons and so on. And we have photons. We have neutrinos. We have whatever you want. We have electrons. And so there are not many of them, but there are some of them. And when I jump here, if the Higgs field jumps from of order 100 GeV to 10 to the 15 GeV, then the mass of electrons that are flying, happily around suddenly jumps. What does it mean that the bubble hits you? The mass of the electron jumps by, whatever, 10 to the 14, a factor of 10 to the 14. And the question is, what are you talking about? Can you ignore this? Is this important or not? Let's calculate if it is important or not and how to think on it. And this calculation is especially important in the early universe. And so I feel happy about doing this. This is solid particle cosmology, finally, that I can calculate with you. So let's call this thermal effect. Although I'm going to give you tools to deal with states that are not thermal. You will see it, but the first calculation to do is in a thermal state. And let's think about what is really the effective structure of this potential early on when in the early universe, when you take back expansion, the density of electrons grows by a lot, like the volume, right? So it grows like redshift cubed. And so if you went early on, you would think this effect from electrons and particles in the plasma is even more important. So that's really where I'm aiming, to the state where the particle density was very high. And I want to ask, this discussion was done essentially in the vacuum state. We did the calculation, and the calculation included 0-point fluctuations, which is the empty Minkowski state, right? And nothing else. And when we included the quantum fluctuations, it was not silly. It actually had a big impact, right? It was exactly particle fluctuation, 0-point fluctuations of the empty state that gave us this entire structure. So now what happens? Do I need to add, or how do I add, corrections due to the fact that I'm not in an empty state? I actually have a lot of particles around. This is the exercise that we want to do. So what is this correction that we would like to add to the potential? This is such an important result that I'm going to derive it in 2 ways. And in the lecture notes that I provided, I derive it in 3.5. But one of them is too technical. So we will not be too technical, I think. So what is it that we are thinking about? We have this gas of particles flying around. And this is simply a statement about the state of the system that is richer than the empty state that we considered so far. Now, the question is, what can I expect from the reaction of this state to changing some parameter of the theory, right? The mass of the particles of this state. And one way to see what this state does is to consider what is the free energy for this gas of particles. Very early on in the early universe, this gas of particles is in a thermal state, right? So if you want the phase space distribution function, the number of particles in a chunk d3x, d3k, and I add this 2 pi cubed because I want to keep h bar equal to 1. So the number of particles in this chunk of phase space is equal to the size of the chunk of the volume in phase space times some phase space distribution function, f of k. And if the system is in a thermal distribution, then this f of k is just the Boltzmann or Fermi-Dirac distribution. So it will be the Einstein or Fermi-Dirac distribution. So it will be e to the beta omega k minus or plus 1. Well, actually, why don't I do this? Well, minus is for bosons, and plus is for fermions. So that is the state we're going to be talking about. And what we want to consider is the free energy of the system. In a way, you can think of the potential that we wrote already as the free energy for the scalar field itself, but the total system has all these particles in them, so you would think that I would want to have F equals VT. Then what would happen? We will calculate this F, and we would ask, where is the minimum? Where does the system want to be? If you have some state indicator that tells you where the system is, the relevant state parameter we care about here is the value of the background scalar field. And so we expect that the minimum of the total system, we expect that the derivative, or what do we want from this potential to do? We want this potential to satisfy the dVf by d phi c equals 0 at a minimum. Oh, extremum, right? Minimum. That's what we want this function to do. This function does it already, we saw, without the VT. If we add the free energy, then minimizing this free energy will also be consistent with the gas. That's what the gas will do itself. So that's what we want to do. What is the free energy of this gas? The question, what is the free energy of the gas, depends on the system we are interested in. We have an infinite homogeneous universe in this exercise. In an infinite homogeneous universe, a chunk of infinite homogeneous universe behaves like a closed system. It's easy to convince yourself that that is true, because if you're in an infinite homogeneous system and some particles go out of your volume, other particles must be coming in exactly compensating it. That's the thing of the state being homogeneous. So in fact, take any chunk you want, it's effectively a closed system. Whatever goes out comes back in. In this case, what you have is a grand canonical ensemble. And so this F should be the energy density rho minus the entropy times temperature. This will be the free energy that you want to look at. In the thermal state, it's a very fun exercise to derive that the entropy for a quantum non-interacting gas, this will be our first exercise. You can add interactions later if you want. We will start with the simplest thing. Let's look at the quantum non-interacting gas. Then this S is rho plus P over T. This is really a fun exercise. Let me write on the side, just so you know that there is no magic here. This is the same entropy, the same pressure, the same energy density that you learned in undergrad statistical mechanics. We are doing no magics. So let me just explain you where this relation comes from. So what I'm really using is the following thing. So consider, for example, a gas of quantum, or quantum gas of scalars. Then this system has a partition function, Z, which is the product on all microstate, all energy state for particles in this gas. Because these are bosons, for each of them, there can be an arbitrary number of particles in each state. So you count the particles from 0 to infinity. And here you have e to the minus ni beta ei. This is the partition function, just to remind. And now this is just equal to the pi on the states of 1 over 1 minus e to the minus beta e. Ei is the energy of the state. And now what you want to do, this product is a little bit formal. It has to go over all the microstate of the system. So consider the fact that our states are non-interacting particles. They are just plane waves or particles with definite momentum k. And so it's convenient to take the log of this object. And you can see that the log of this object is minus the volume of the chunk you're looking at times d3k 2 pi 3, and just the log of this object, beta m squared plus k squared. I will call it m particle, because I used I, unfortunately, plus k squared. So E k is what I always call omega k is the square root m squared plus k squared. So these are the states at definite momentum. They have this energy. And I should have defined, I'm sure you remember, this beta is always defined as 1 over t. Just a nice convention. So this is the log of the partition function. For this, you can take the entropy from your textbooks. This is 1 over v d by dt of log z. And now my exercise for you, it's just playing with integrals. It's really fun exercise. I suggest to do it. Use our distribution function. So use our distribution function f being equal to 1 over e to the beta omega minus 1 for bosons, and show that this object is exactly equal to rho plus p over t, where you simply write the equation for the energy density and momentum of this kind of gas of free propagating bosons. I'm going to give you the expression for p because we're going to need it later, so it will appear later on the board and you can use it to the exercise. Otherwise, you can remind yourself. So that's the exercise to do, and this will be the answer. Nicely, if you repeat the exact same exercise, but now for the ground partition function for fermions, fermions have a similar thing. So this is bosons. And Z for fermions have only 2 states. They're either on or off. That's what they can do. So the Z is the product on microstates times 1 plus e to the minus beta ei. Repeat exactly the same exercise with the same definitions, but with the plus in the distribution function, and you're going to get the same result. So that's homework. So there is no magic here. We are honestly and literally calculating the free energy of this gas of free particles. OK. So very good. If this is the thermal state, then I know what F is. And this F is just equal, according to Grosjean law. The equality happens at the edge of the blackboard. And it's just minus the pressure. And again, if you remind yourself, the free energy of a grand canonical gas like this is minus the pressure. This is the Gibbs free energy. This is what we need here. And this is what we get. So a first guess, a natural guess, for you to decide what the VT that you should put in here is just minus the pressure of this gas. Let's calculate what this pressure is. Do you remember what pressure is? Who remembers what pressure is? Okay, the rate of collisions of the wall, let's remind what it is, because this is such an important result in cosmology. Why don't we do it kind of from the grassroots, right? So what is pressure for a bunch of gas? Here is what pressure is, okay, when you teach your students. Unless I screw it up, then it's not what it is. We should see. Take this infinite bunch of gas, right, or a system full of gas, and construct a box in this. Right? Construct a box with some particles in the box. Now bring your vacuum pump and get rid of all the gas outside. Keep all the gas inside of the box. Now, obviously, the particles inside the box are hitting the walls of the box, and the box better be strong for it not to break down. Pressure is the force per unit area of wall that you need to hold the box in place. So pressure is force per unit area. This is all it is, and this is what it is for our gas. Let's compute it. Okay, so the force is, of course, the same on any of the sides of the box. Let's compute it on one of these sides of the box. So what will happen to the box, like it was suggested here, is that particles are flying around. They're flying around in all directions. Let me draw this like they're velocity vectors, right? The force across the wall, the force, F, force, is momentum change per unit time. It's the amount of momentum that a particle exchanges with the side of the box when it collides with the box per unit time, because momentum is being exchanged all the time by particle collision. So, but in general, force is momentum change per unit time. A given particle that comes and hits my wall, I'm doing a very simple treatment of this, but it doesn't matter, the details are not important, is going to bounce back from my ideal wall. What does it mean? It's going to reverse its direction. Let's call this the x direction. It's going to reverse its momentum in the x direction. We will do this relativistically, actually. Why not? So each one of these particles that comes in with momentum, let's say kx, it also has momenta in the y direction and some momentum in the z direction, but those don't talk to my wall. My wall is on the x direction, right? I don't care that it's coming at an angle. All I care is on the x component. That's the only part of the momentum that will change. So my particle has some momentum kx when it comes in. The momentum that it transfers to my box is twice this, because it came with that momentum and was launched back with the opposite. So I have twice of this. That's the amount of momentum per particle. And now, how many particles are hitting my wall per unit time? So basically, all the particles in an interval of time dt, the number of particles that are going to hit my walls are those particles that are at a distance delta x equal to the velocity in the x direction of the particle times delta t. That's the distance from my wall at which in time delta t, all the particles within this region, right? All the particles, in fact, within this volume. Oops, how do I draw this? It's horrible. Good. Inside of this volume of length side delta x, let's call this the side of my box A, just the area. Inside of this volume, all of the particles that were moving in the right direction are going to scatter off my wall. Particles that are farther out at velocity vx are too far. They're not going to reach my wall within time dt. Very good. And so the number of particles that are colliding with my wall at time dt is just given by the phase space distribution function. Okay? So the total momentum is the sum on all of these particles. So the total force that I have is the area times delta t times an integral over all the velocities, d3k 2 pi cubed. Let me limit my integral, because I only care about particles that have kx larger than 0. Only those people that are flying to the right are those I care about. Each one of those particles, well, how many do I have? This is the size. This times V is the size of the volume. So this is Vx. Now Vx delta TA is the volume of the box. This is the volume in momentum space that I want. I want F of K. Now it's the number of particles in my box. Each one of them is delivering to me 2 kx momentum. So that's my force. However, you see this restriction on positive kx and the factor of 2 from the amount of momentum I exchange, I can just drop this restriction and drop the factor of 2. They will cancel, right? So I can just sum all particles, even those moving in the opposite direction, and this will take care of this factor of 2. So what I have is A delta T, D3K 2 pi cubed, F of K. Now, who remembers what's a relativistic velocity? If you have momentum K, momentum if you want, the momentum in the x-axis Kx, what is the relativistic velocity Vx? It involves the momentum and the energy. Who remembers what it is? It's proportional to the momentum, obviously. But I need to multiply or divide it by something. Remember? Not mass, because it's relativistic. You're totally right. If the particle was not relativistic, you would take momentum and divide by mass to get velocity. This is relativistic mechanics, so you need to divide by energy. This is the velocity. So what I have here is, in fact, kx squared divided by omega k, because I had Vx times kx. I dropped the factor of 2, and I dropped my restriction, and that's what I got. But our gas is isotropic and homogeneous. And so this is a sum only on the x component, because in my imaginary box, I consider the side on the x side. Just to make my life simple, let me sum on all components and divide by 3. The average of the pressure in all directions is the same, right? So now this is kx squared plus ky squared plus kz squared. All of them give the same result, and I divide by 3 to compensate. And I'm done. And I can write what my pressure is. And my pressure is just this expression. To get the pressure, divide by the force by A and dt. And that's it. So this is minus a third d3k over 2 pi. Whoops. 3 k squared over omega k f of k. Questions? Yes? If there is, I made a mistake and we fix it. You mean these two? It's not, because I dropped the restriction. You see, in this integral, the y and z I summed from minus infinity to plus infinity, but the x I summed from 0 to plus infinity because of this restriction. Dropping it, I sum the x from minus infinity to infinity, but I have to compensate by a half. The half eats the 2. Thanks a lot. Thanks for the question. Don't hesitate to ask. I'm trying to do something simple. And again, if you don't understand, it's my fault. But if you don't understand because you didn't ask, it kind of begins to be your fault. Spectacular. And now we see, in fact, I could stop here for the purpose of our discussion, because this function does indeed depend on the field. In the standard model gas, in the standard model plasma, like Christophe said, for example, the mass of the top quark is equal to the Yukawa of the top times phi c divided by square root of 2. The mass of the W is similarly proportional to phi c. So the masses of these particles that are flying around are proportional to the field. And everywhere here, we have omega k, which is the square root of k squared plus m particle. I don't know how to call it. Let's do this for our bosonic field, little phi. So it will be m phi squared of phi c. And our f's are what is written here, and they have omega again. So the pressure of the gas obviously depends on the masses of the particles, and the masses of the particles depend on the field. And so we got ourselves a function that is certainly interesting and contributes to the effective structure of the potential. This is coming from the state. I was asked before, does the structure of the potential change? Well, you can think on it as any way you want. We think on it in terms of an effective potential. The quantum mechanical zero temperature or zero particles configuration is still there. It's just that there are more degrees of freedom involved, all these thermal particles, and so effectively the equation of motion will change. And I can swallow it by defining an effective potential. If you want, you can think that the structure is changing in time, or in redshift, or in temperature of particles. If not, you can add it. I mean, think on it whichever way you want. Let's just write what this expression is, because again, it is so important, and you will see it in textbooks and so on. So this is minus a third d3k 2 pi cubed. Let's call it m phi squared. So when I write m phi squared, I'm really only considering the Higgs fluctuations, the quantum irreducible quantum fluctuations of the scalar field itself. But in general, you would need to add to this all the particles that are in the plasma, right? That is easy to do mentally. Just sum everything else if there are other things. So I have this, and here I have e to the beta minus 1. This is worth massaging a bit. This is for later use for me. So this is actually worth massaging a bit. But to save time, I will skip some of the details. So again, a little bit of integrals for you to do. This object is equal to minus t to the 4 x squared. So if this stuff kind of stands together, let me split things. Here we go. Without the minus, because I did v, which is minus p. What I did, all I did that you can easily verify for yourself, I just changed the variables to dimensionless variable x by just changing from the variable k to the variable k over t, or beta k. So x is just beta k. This pulls out a factor of t to the 4, which shows that we have the correct dimensionality. What we want is an object that is energy to the 4, or energy density, which is exactly what pressure is. Force per unit area is exactly energy per unit volume. This object here is where the dependence on m phi squared enters. And you can see that the only dependence on the scalar field, or the properties of the particles, is through the combination beta times m, or m phi divided by t. This is fun. I suggest you do it. OK, this was the first derivation. I like it. It's a little bit mysterious in the sense that it doesn't make contact in a clear way with what we did for the zero temperature effective potential. We just said, I told you, let's add the free energy. So because this result is so important, before I go ahead and investigate what it actually means, which is what I plan to do in the rest, in later part of the lecture, I would want to derive it yet again in a totally different way. OK? So those who are bored can go get coffee. But let's derive it in a totally different way. I think this is such an important result. It's worth it. In fact, we looked at zero-point fluctuations in canonical quantization. So why don't we derive the exact same things in canonical quantization? And the main thing that this, to me, makes clear is that the object we're seeing here is a property of the state. We have made a very strong assumption that is valid for the standard model at high temperature, which is that the state of the gas is this thermal state. how would the effective potential look like if the state was different? For example, the gas could be out of thermal equilibrium. For example, what if you have those massive particles flying around, but in fact, as you know, it's possible for particles to decouple, to freeze out. Who have heard the notion of freeze out in the early universe? Great, many of you have heard it. So the particles could be out of thermal equilibrium, in which case their distribution functions would assume a different shape. What then is the effective potential? The tool I'll give you now allows you to compute it. So let's rederive this. Let's call this what we did here, let's say thermodynamic derivation. And now we will do canonical quantization. I will do it in a way that is similar to the way Vyacheslav Mukhanov does it in his book on cosmology. So if you want to look for a book, look at Mukhanov's book. I like it. So let's start with the classical equation of motion of a scalar field. So again, we're going to have ourselves our scalar field. It has some background, plus in principle, quantum fluctuation. So in other words, if you find yourself in this universe and you see the field configuration in one realization of this world, when you visit it the first time, who knows which time it is now, right? But when you visit it the first time, you'll find some classical average value plus some fluctuation on top. That is what this var phi means. When you visit it again next time, this will be the same and this will be different. And we're going to canonically quantize this field, but it's convenient to start with its equation of motion. So the equation of motion, I've been neglecting expansion. Let me, for a moment, bring expansion back. I may use it another time, but this is not crucial for us. So the equation of motion in an expanding universe for the field looks like this. And that on average should be equal to 0. In other words, you take my field configuration phi. At the classical level, this equation says that if you place my field somewhere that is far away from a minimum or an extremum, far away from a point where dv by dphi is 0, then my field is going to roll, and it's going to roll satisfying this equation of motion, where in a non-trivial expanding background, this g is non-trivial. I said that about g, that's the last I'm going to need it. I'm not going to actually use it. So what we're going to do is simply take this equation and expand phi around the fluctuations. Okay, so let's just take this phi and expand it in our fluctuations. And then we're going to take expectation value of the equation we got, and we're going to ask that on average it is 0. Okay? So if I expand, what I have the equation of motion of phi c, just copy paste this equation of motion and plug phi c inside, of course, plus the derivative term for phi, for var phi, okay? This term is the linear part in the expansion in fluctuations. And then there is a second order part. The kinetic term doesn't have a second order part because it started as a linear part of the field. So the really interesting part for us comes from the potential, which is in general a nonlinear function. And so it will have another correction. And this correction is half. This was already dv by dphi. For the var phi squared correction, I'm going to go to the third derivative of the potential, right? This was the second for the linear term, and now we need to take the second derivative of this. So this is d v naught cubed by d phi 3 at phi c times phi squared. To all of this object, I'm going to take a quantum expectation value. So let me do this. And on average, this should be 0. Here there is a quantum expectation value. And here there is a quantum expectation value of the classical equation of motion, which just gives it back. Yes?
Why are we using V naught for this derivation instead of the effective potential?
Yeah, the question is, why are we using V naught?
Yeah, no.
Because what I'm going to do now is quantize it the first time, if you want. So what you do expect to see that in my derivation here, and that's one of the points for why I'm doing this, you expect to find V1.
Okay.
And you will.
Okay, perfect, thanks.
Yeah, very good question. Thank you very much. So here is the thing. The entire premise of this discussion is that the expectation value of the equation of motion, or the expectation value of the linear power of phi is 0. So the expectation value of the field is phi c. This is exactly what we want from phi c to do. The expectation value of var phi is 0. And therefore, this entire term on average is 0. I don't erase it because I'm going to need it in a moment. But for our equation, this entire term goes to 0. And so expectation value of something squared might not be 0 and will not be 0. But what we see is that given that that is 0, our effective equation of motion is the original one plus something proportional to expectation value of phi squared. Another comment to notice, look at this crazy third derivative of the potential. It's not an incident. It's not by accident that it is a third derivative. The second derivative of a potential would be the mass term. Interactions, nonlinear interactions will only begin to appear at higher orders. So the first time you feel interactions is at the third derivative, and that's where we got them. Okay, second derivative would belong to something else. It's not interacting, just free particles. So effectively what we have, let us consider regions in the potential where I can ignore the derivative term. Let's look for minima of the potential and ask, what is it that we're minimizing? What it is that we're minimizing is this, dv naught by d phi plus a half d3 v naught by d phi cubed. I can put phi c everywhere. These are function of phi c time expectation value of phi squared. This is the object that we are trying to minimize. In fact, sorry, why don't I call this d by d phi c of v effective? This is the object that we want to set to 0. And this is the new contribution that we had. So that's what we have to compute. What is cute about this is that unlike in the thermodynamic derivation, I didn't need to specify at this point what was the quantum state of var phi. In fact, defining the quantum state is the same as specifying what is the expectation value of phi squared. So now let's play with this a little bit. How do I manage to have no blackboard? I don't understand. It's so big. The more they give you, the more you commit. So I want to compute this object. Any questions? OK. Let's start with this expectation value. And as I said, we're doing canonical quantization. So let's quantize this field. I'm going to ignore expansion for this part of the exercise. We can restore it back. The process we are looking at is a hot universe that's expanding slowly on particle timescales. So the distribution functions are something, for example, in the simple exercise, close to thermal, otherwise whatever they are, but I'm ignoring the expansion in the exercise, just to make my life easy. And I would like to understand what is phi squared. So let's quantize our field. It's just a scalar field. There is nothing to it. You know the quantization of the scalar field. It looks like this, d3k, right? ikx. Peskin and Schroeder, first page, something like that. So we quantize this object. up to horrible typos, of course. And canonical quantization amounts to imposing, so there is phi, there is the canonical variable, which is here just phi dot, and you can write it if you want. They obey canonical quantization, commutation relation. These canonical commutation relations are satisfied by imposing canonical commutation relation for these guys, which is A, K, with A dagger, no place. Let's call it P. And all other commutators vanish. So let's start with the empty state and see if we recover what we did before. Okay, so let's start with the empty Minkowski vacuum state. Let me call that vacuum state 0. That state has no particles, hence we call it 0. It has 0 particles, yes?
Just to have sure, you still consider real fields, right?
Mm-hmm.
Okay, nice. Thank you.
This is just a real massive scalar field. It has the usual omega k, and in the background of phi c, the mass of this field is, just to remind you, phi c squared, and v naught for us was m squared half phi c squared plus lambda over 4 phi c to the 4. This is literally the same system I was working on before, right? I didn't need to specify it so far, but let's specify it now, so we can match to other things. So this is the empty state. What does it mean it's the empty state? It means that the particle number operator acting on this state is 0, and also just any lowering operator, actually, with anything behind it, acting on this empty state is 0. So you can calculate under the empty Minkowski state, not this interesting thermal state, right? First, a very simple state. In this empty Minkowski state, what is the expectation value of phi squared? So now I define what I mean, the expectation value under 0. And if you plug this in and use the commutation relation, what you're going to find, let me do it schematically, you're going to find 0. And just schematically, there will be 2 integrals with everything, right? There would be AK plus A dagger K. And there would be, I already write just the K. If you want, you can write P and keep the integrals. They will keep the thing diagonal, right? Under 0. So this is 0. I do all this for a reason, I think. So there will be AA plus A dagger, and then there will be A dagger, and then there will be A dagger A, like you know, under 0. Under empty Minkowski state, these people go to 0. This also goes to 0 because it has an A lowering operator acting on the vacuum. Only this object remains. You can add and subtract this thing to make it a commutator. And so the answer of this object is d3k over 2 pi cubed. There were 2 powers of square root 2 omega k. They become just 2 omega k because the square root goes away. So there is 2 omega k. And I believe this is all there is to it. There is a half. Yes, I wrote the half. OK. Very good. So that's what this thing is in the empty Minkowski space. Of course, this integral diverges and so on. This divergence is only a property of the vacuum fluctuations. I'm not going to worry about it. Let me just check what it is. Okay, so imagine that this is a cyclic situation. I'm going to go here. Cyclic universe. So, phi squared under the 0 state is this. Our correction, let's call it delta V, this term, this is the new term. This was V0. We know what it is. This is the new term. That's the part that depends on phi squared. So that's what I need to compute. Let's call it for a moment delta V. So my delta V is a half d3 V0 by d phi c cubed times that. What is the third derivative of V? You know this. You already know that the second derivative of V0 with respect to d phi c squared, this is exactly m phi squared of phi c, which is m squared plus 3 lambda phi c squared. So this object is exactly a half d by d phi c of m phi squared times a half blah, blah, blah. Let me play with this object just a very little bit. So a fun thing to do, sorry, why did I write it like that? That's very confusing. dm phi squared by dvc. So the fun thing that I can do, I have here an m phi squared. What am I really looking for? You see, the object on the left is d by d phi of something. What I'm really looking for to find is that this crazy thing will become d by d phi c of some extra contribution to the potential, right? The entire sum of these terms should become an extra contribution to the potential. So to be more precise, I was not careful here. What I really had is d by d phi c, right? Thanks very much. So the exercise that you can do, you can just introduce the fake integral and take it out. So a half dm phi squared by d phi c, d by d m phi c squared, integral dm squared half. I hope this is clear. The only thing I did, I took this object and I integrated it and took a derivative at the same time, right? So this is just another way to write the same object. The reason this is a little bit fun, because look at what I have here. Here I have dm phi squared by d phi times d by dm phi squared. By the chain rule, this entire object is just d by d phi. How did I get out of Blackboard? It's unbelievable. So I'm going to skip a step. It's in my note. You can do it yourself, basically because I'm out of Blackboard. What you have, you can immediately check after one integration by part that the thing that is written here is exactly d by d phi, d3k 2 pi cubed, half square root m phi squared plus k squared. Now, we all should be very happy. Why should we be very happy? At least I should be relieved and happy. The reason I'm relieved and happy is because the thing we're taking a derivative of is exactly the 0-point energy. This is where we started from yesterday. So indeed, our Mukhanov trick gave us exactly the contribution such that, in fact, we identified this delta V that we did under empty Minkowski space was exactly V1 we had before, right? So VF, V0 plus V1. Our method recovers V1 for the vacuum fluctuations. Now, maybe we have some confidence. We can go ahead and ask what's the rest, right? If the actual state will also have fluctuations on top of it. Questions so far? All right. So let's start to put the new things in. Great. Yes, OK. Well, the reason I needed this, I didn't comment about it. But the reason I needed this equation of motion is that when I quantized my system, of course, I was using this equation of motion. Okay, that's something I should have commented. I even took the trouble to put this yellow thing here for this. So this canonical quantization is canonical under this Hamiltonian. This is a free Klein-Gordon equation with just the m phi squared in front. Okay, so when we quantize exactly this equation. So I already used it, and you didn't complain, so I can erase it. And my task is very obvious. My task is just to calculate now the expectation value of the square of var phi under a more interesting state. So I need this under interesting state. And let's start with the first interesting state that we have, which is the thermal state. Why don't I call the thermal state T? A thermal state is not a pure state, as you know. It's an ensemble. You're familiar with this. I mean, I won't remind you here. But basically, it says that it contains particle excitations of all wave modes with the Boltzmann factor. That's what it does. So that's the thermal state. Under this state, I'm going to need to compute half d3 v naught. So we need to compute dm var phi squared by d phi c, which is this object, phi squared. And this we expect to be d by d phi c over vt. Let's go back here and consider our state now. So now our state is thermal. Oof. What happens under the thermal state? Now, the number operator doesn't give you 0 under the thermal state. More precisely, if I put my thermal state here, then the only difference from the Minkowski state is that A dagger A now needs to give me the number of particles. It's the number operator. It counts the number of particles around momentum K. So the correct definition to make this the properly normalized thermal state is to say the expectation value of the number operator is 2 pi cubed. Don't worry too much about pi's. Delta 3, let's call it k prime, k minus k prime, f of k. This will make sure that the expectation value of the number operator gives me the correct number of particles around this particular momentum mode. At the same time, there are no off-diagonal elements. So let me write the same thing that I did before. The only thing I need to do is to replace 0 by t. Oh, wow. Time runs when you're having fun. So replace 0 by t. I do exactly the same exercise. These people die, just like they died before, because they're off diagonal. These people take the thermal state on the right and kill 2 particles in it. Although it has a lot of particles, it is an ensemble. There are no interferences between a state with, say, 3 particles and a state with 1. And so if you kill 2 particles, you're dead in this expectation value. So these are gone. This is the number operator. It's not gone. Moreover, you have to be a little bit careful about this AA dagger because it's not a commutator yet. What is it? So what we have A dagger plus A dagger A. This is the commutator of A and A dagger, which is just the quantum commutator as usual, plus 2 A dagger A. I add and subtract an A dagger A to make this a commutator. And so now I know what to do with this. This is just the commutator plus 2. This part of the exercise stays exactly the same. But what I have here is a half from my commutator, so that half that was here before, plus f of k. That's all. This little half that separates vacuum fluctuations from the phase space distribution function is exactly from this exercise with the commutator. And now we're really ready. This object we already did. It's the complicated part with divergences and whatnot. This object will be completely finite, and this is the thermal part. And so I can recognize the thermal contribution, dVt by d phi c. It's just the part coming from F. So it's a half dm phi squared by d phi c, the same thing here, and the part coming from F, which is d3k over 2 pi cubed f of k over omega k. OK, I have 5 minutes. Oh my God. So I will simply not do this integral. I leave you the integral to do. There is nothing there now. There is no thinking anymore, just crunching through this integral. Hint, do my trick of inserting a derivative in an integral with respect to this auxiliary m squared. It helps. After you crunch to this exercise, you find exactly what you would expect, which this is d by d phi c. You already know how it comes about, of exactly this object that I will not write again. OK? It looks like a big jump, but it's just a tiny little technical integral that you need to do. Just integrate this, and you get the same. So what happened here? We derive the thermal effective potential using 2 different ways, thermodynamic and canonical quantization. We get the same answer. And I have the entirety of 5 minutes to discuss what this is, the actually interesting physics. OK? But maybe the derivation was something that you haven't seen elsewhere. Questions before we discuss what this actually does? Yes?
The infinite part doesn't matter?
Well,
because
so
it was
the
one
part
infinite
of
part,
what?
and now are
This is
2
an
infinite
infinite
part.
part.
Yeah.
This, it matters a lot, and you have to deal with it. And I kind of broke my head about this yesterday. This we dealt with. It is exactly the same infinite part that we had at 0 temperature.
Yeah.
You're right. It's important. You have to regularize, renormalize, all these complicated things. The crucial thing to see is that the thermal part is completely finite because it has a natural UV cutoff. It has some divergences, but not UV divergences. And in fact, you can see it anywhere you want. Let's see it here. So you see there is this exponent. If you take this integral at very large k, you have exponential suppression. This exponential suppression is exactly Boltzmann suppression. That's all there is to it. So the thermal potential is completely UV finite. I don't have to worry about infinities. I have to worry about infinities for the zero temperature potential, but I kind of worried about this yesterday.
Okay.
More questions? If not, let's discuss in 2 minutes what this does, because it's really easy, actually, to see what this does. The details, I think, are important, but not very deep, and you can easily do it yourself. So this is VT. Let me go back to my picture. Actually, let me do something quick before that. Can erase everything, and we got the expression we wanted. Now, the question of how this VT behaves as a function of phi c, right? How does the effective potential behave like in field space is just a numerical question. You can take this integral, put it in Mathematica, and calculate what's the shape of the potential. There is nothing to it. Use the Coleman-Weinberg for zero temperature, and add this. There is, as an aside, no closed form answer for this integral. So that's anyway the best you can do in general, if you want to consider everywhere in field space. However, the most interesting regime maybe is the high temperature regime, high T. High T means that m phi squared over T squared, which is beta squared. M phi squared, the thing that is sitting here, is much, much smaller than 1. Whoever your particle is, if the temperature is large enough, it will enter this high temperature regime. In this high temperature regime, there is a small parameter. Beta m is a small parameter. So we can expand this object as a function of beta m. And if we do, then at high T, this V of T becomes, I will write the answer for both boson and fermions. That's the other little thing that you can remember. I could have repeated exactly the same exercise for bosons and fermions. The only difference would have been that I would want to use anti-commutation relations on this object. But in fact, and what they do is they just put this minus into plus, and they add the plus in front for fermions. That's all. You can easily repeat this calculation. So the answer is for bosons and for fermions, that this VT looks like T to the 4 anyway. You see there is the T to the 4 in front, which is also nice and cute, because when you take the limit T goes to 0, you can verify that this thing is not singular. It goes to 0 when T goes to 0, okay? As it should be. So it looks like T to the 4, and here there is minus pi squared over 90 plus beta squared m squared over 24 minus something plus higher orders of beta m, okay? This plus and minus, people make a fuss about it for some reason. I may, if I want, maybe if we want, maybe I comment about this tomorrow. For fermions, very similar. Plus stuff, higher orders in beta m. What is happening here? This is for 1 degree of freedom. Let's write here Gi, Gi. The numbers of degrees of freedom. For our 5 fluctuations, there is 1 degree of freedom. For the top quark, there are 12 degrees of freedom. 4 spin and 3 color. Fair enough, you just add the degree of freedom in front. What is happening? At very high temperature, what our effective potential does at small fields, I should draw quickly. Remember our picture? Our picture was this, and something far away. Very high temperature limit also means the particles' masses are small compared to temperature, so we're interested in this region. The field phi is not so big. We're looking the effect where the region where this expansion is valid is when m is small, so phi c is not so big. So it's happening here. What is happening to us is that both the boson case and the fermion case, the VT subtracts for you, or it gives for you an extra negative constant that scales like T to the 4. That's the first thing that happens. This is only valid at small field or small masses high T. It will do something like this. It's going to take your potential a little bit down. If you make the temperature even higher and higher and higher, it's going to take your potential further down and down, just adding near the origin a constant. You cannot treat this constant everywhere in field space, because far away in field space, this expansion isn't right. In fact, I could plot these expansions. If I only plotted Vt as a function of phi c, it would look something, it's negative, okay? But it looks something like this. It saturates exponentially to 0 at very high T because of the Boltzmann suppression. When I go far in phi c, the mass or the energy is arbitrarily large, and this thing dies exponentially. And it falls down with this first leading term at small masses, okay, or at small phi. So that's this term, and that's what it does. In the total picture, it effectively lowers the origin. The next correction that it has is this extra m squared. For a top quark, for example, if you consider the contribution here from the top quark, this m top squared is proportional, is y top squared over 2, phi c squared. That contribution is positive. So it is adding for us a positive phi squared dependence to the field in addition. So the shape here is like that, okay? And then there are higher order terms that are, as I said, a little bit interesting, but I don't have time to discuss. The general structure is this. The constant negative term is exactly the pressure of a non-interacting gas of bosonic or fermionic quantum particles. That's exactly the usual thermodynamic pressure, as we expected. Leading contribution in the relativistic regime, where the mass is small compared to temperature, is just the pressure of massless gas. These are the mass corrections to the pressure. What is happening to us is that near the origin, where the particles become nearly massless, we enjoy more entropy. The free energy becomes small. And so the system is driven to fall in this direction. So in particular, in the standard model, we know that today we live here. But when we crank the temperature of the universe higher and higher in the early Big Bang, these thermal corrections for the standard model plasma inevitably, for all the types of particles, restabilize the origin, right? The origin was unstable. At 0 temperature, it becomes stable. And so in this kind of model, in a chiral model where masses are proportional to the field, inevitably, if you crank the temperature high enough, you will have symmetry restoration. High T. This is symmetry restoration. It says that in the very early universe, on very general, not completely bulletproof general, but very general grounds, free energy prefers this symmetric point where more particles are massless, the pressure is larger, and the state of the system moves here. And in fact, at very high temperature, you expect the vacuum expectation value of the Higgs field to be 0. An important phenomena in particle cosmology, a comment that I want to add, just to finish, I'm a little late. Here is the comment that I want to add, and that concludes this discussion of vacuum energy that we started in the first day. We already saw that today at 0 temperature, it was measured by cosmology that the vacuum where we are is extremely degenerate with absolute 0 cosmological constant, or vacuum energy density was very, very nearly, but not just exactly 0. This was that state. The high temperature state lives at 0 field. It feels this effective potential that brings it to the origin. When it brings the field to the origin, though, if you ask what part of this energy density is scalar field, real cosmological constant energy density, that part is actually given here. Our state variable moves here, and now it lives here at very high temperature. Remember, this extra negative term of the free energy is not a cosmological constant. This extra negative term is, in fact, thermal pressure. This is relativistic particles. This is just radiation pressure. Radiation is not a cosmological constant. It's something else. Gravity responds to all of them by the Friedmann equations. By the way, in a way that depends on the equation of state. The equation of state, as the temperature changes and the universe expands, for this object and for the scalar field just sitting where it is, the equation of state is different. Okay? So as we move here, the cosmological constant goes up in the early universe by about 55 orders of magnitude due to this symmetry restoration. The fact that it goes up is masked to gravity by the thermal energy of the hot gas. So expansion doesn't care much. Expansion sees mostly just the pressure of the gas or the thermal energy of the gas. But the constant part is not even constant. It moves back and it lives here 55 orders of magnitude. So when we discussed in the beginning, there was a question several times, what is the time changing of the cosmological constant? In the standard model, no fancy new physics, cosmological constant made a dive from 55 orders of magnitude above where it is today, all the way down to just exactly 55 orders of magnitude, 10 to the minus 55 above 0. Okay? So in some sense, this may, I don't have anything smart or encouraging to say about this observation, but it's an interesting observation to make. You could think somehow the universe knows today to stop just before 0. Well, it somehow knew that even when the state of the field was very, very far from 0. Right? This thing was ready to catch you when you fall. You were not here, and then you moved. Okay? Everybody looks either, maybe you're hungry. So this concludes, I think, my discussion of the cosmological constant, and it explains the time evolution where we were before. Of course, you can generalize this to more degrees of freedom, more scalar fields, and so on. You just repeat the same exercise. You can generalize what you do to other states, not the thermal state. It's easy. There is in my notes an example. All you have to do is compute the correct expectation value of the number operators. Okay? And I think I will stop.
Thank you. So, questions?
It's late.
People are hungry? People are puzzled? Okay, you can think over and, well, we don't have discussion sessions today, but we have tomorrow. So, but anyways, I'm sure Kfir can answer questions during coffee breaks and things like that. Okay, so let's thank Kfir again. And